This is Robert Austin. Robert Austin is a physicist. He works as an adjunct here at St. Petersburg College at the Clearwater campus, and he works for a company called Constellation. And Robert, you were going to tell me a little bit about Constellation and what you do there and what the company does.
Well, Constellation's a small company, employs around 40 people, biologists, chemists, and I'm probably the lone physicist. And I'm working in the nuclear detection area at Constellation, developing or helping develop detectors for gamma radiation primarily and neutrons.
So how does that technology actually end up working? What does it do exactly?
Well, there's two technologies I've been involved in. The one I came to Constellation to work on was high pressure xenon ionization counters. These are, it's like a very high quality Geiger counter. It's filled with high pressure xenon gas, which is a very dense gas, and it stops radiation efficiently. And what makes it different from a Geiger counter is that a Geiger counter just tells you when something happens. You know, if radiation encounters the detector, you get a click or a needle, the indicator moves, but an ionization counter tells you the actual energy of the incident radiation. So you get a spectrum, and a spectrum is like a fingerprint. You can identify what the material is that produced that radiation. And this is important in medical imaging and in defense, because specifically in defense they're looking for things coming across our borders, and a lot of these things are innocuous. Could be pottery or bananas. All these things are radioactive actually. It could be the driver of the truck could have had a stress test at the hospital. These things you can pick up with a typical radiation detector, but you don't know what it is. You only know there's radiation. That means you stop the truck, make the person get off the vehicle, do a search. It stops traffic, it slows everything down. If you can actually identify what it is, and in most cases it's something innocent, and you just say, go on. You know, there's some radiation there, but we know what it is and it's not dangerous.
Is this a technology that's already in use in some fashion, or is this something kind of newer than that?
It's not really, for Homeland Security it's not widely used. It's been looked into and it's been very difficult to get it accepted. This technology is used in mostly for the xenon specifically, mostly in basic science research, astrophysics. There's experiments, deep underground experiments looking for dark matter in the universe. These employ similar kinds of detectors.
Now this, I don't know whether we actually said this, but this sounds like it's defense-related work or Homeland Security-related work.
Most of our funding is through the DTRA, the Defense Threat Reduction Agency.
Uh-huh.
And we're developing detectors. I mean, I'm working on nuclear detectors, but there's also other people at Constellation working on biological and chemical detectors to be flown on unmanned aerial vehicles, UAVs.
Now, is this anything at all, does this look anything at all like what you thought you'd be doing when you were a young person and thinking about physics as a career?
Only remotely, yeah. Almost as far back as I can remember, at least to the first grade, I knew I wanted to be a scientist. And then over the years, it started with thinking of becoming a chemist, and then it was moved towards engineering or physics. And probably by the time I graduated from high school, I saw myself as becoming a theoretical physicist at an elite university somewhere. And but after finishing my undergraduate education, I felt lost, so I went in the Navy for 2 years, and then came back and went to graduate school at Purdue University, and I didn't look back after that. I worked, but at that point I started realizing I was probably my abilities were more in the direction of experimental physics than theoretical. And I got to work on an experiment very close to my initial interest in cosmic ray physics, and it had the advantage of being located on Mount Haleakala in Maui, so I got to travel to Maui and work on top of a mountain and detect cosmic rays and think about black holes and neutron stars. Those were the things I always wanted to do, and that's what I did my thesis work on. So my thesis was on the search for cosmic rays, for high energy gamma rays from Cygnus X3, which is a powerful X-ray source. And since I realized by the time I started writing it, I wouldn't detect any. We weren't going to detect anything from it. I basically wrote, found an upper limit to the flux, and because we didn't detect it. And I kind of wrote on two subjects on primordial black holes too. There's the idea that after the Big Bang, because of the high densities, matter was compressed. Some matter could have been compressed to densities where it would actually form black holes, and there would be a whole spectrum of masses, and smaller mass black holes, like equivalent mass of Mount Everest, would actually be evaporating around this time, giving bursts of gamma rays which could be detected. So we looked for that, and also probably detected more meteors than we detected any primordial black hole candidates. So that was sort of a negative result too, but it did provide a limit on the number of primordial black holes within a certain distance of the Earth. So.